received the other one? Did we get it?
आइए
वो भी आ गया?
yeah download save
Oh, okay.
download
All right.
save
All right.
to use this.
Do I need this? It's a microphone.
Yeah, for the recording.
Oh, for the recording. Okay, should I start then?
Let me
Okay.
introduce.
Yeah.
Good afternoon, everybody. Thank you so much for joining for the Smart City Seminar first for this academic year. I have the pleasure to introduce Dr. Pushkin Kachroo, who is professor in UNLV, and also he was my PhD advisor during my days at UNLV. So let me give a brief academic journey. I think he'll talk more about it, very interesting. So he did his undergraduate from UCF Bombay in India in civil engineering. Please pay attention to the degrees and the jumps from one department to another. After that, he did his master's in mechanical engineering from Rice University. After that, he went to UCB, Berkeley, to do PhD in mechanical engineering. He went to Virginia Tech as assistant professor in electrical engineering department, and then that's when he did his PhD in mathematics. He joined as a full professor in UNLV in electrical engineering department, and now he's doing his third PhD in quantum logic. Okay, now over to Professor Kachroo.
All right, everybody, thank you so much for allowing me to be here. And it's a pleasure to see Dr. Agarwal at his home, at his den. You want to come in? Oh. Okay, and maybe we'll just wait. Okay, so I will basically talk about a few things. So I've done work in a lot of different areas, and transportation, intelligent transportation systems is one of my main areas of research. And in there, I'll give you a little bit of outline of the kinds of things I've done, but then I will focus on one of my original theoretical contributions in transportation, which is the mathematical modeling of travel time. So I'll talk about that. And then I'll show you something very interesting, again, from a mathematical point of view, of something in traffic dynamics, as well as the dynamics of evolution of a city, right, a city area. So how it evolves and changes, and how that is connected mathematically to how traffic evolves on a highway or on a street and stuff. Okay, so that's the plan. And if you have any questions anytime, just stop me and I'll try to answer it. Okay, so it's just an outline. I'll just skip through the things I'll cover. But I'm just my mathematical journey in a personal mathematical journey, and some topic about intelligent transportation systems and the interdisciplinary nature of it. So as I said, as Dr. Agarwal said, so I did my BTech in IIT Bombay in Civil Engineering Department, and my research, so I had a thesis that was in operations research and transportation planning. Then Rice University, I did in mechanical engineering, robotics and artificial intelligence, and my thesis was on medical bioengineering, essentially a design of a sensor. Then I went to UC Berkeley, did my PhD in mechanical engineering, and my PhD was on autonomous vehicles. So we actually built autonomously running vehicles. That was in 1993, before Google and other companies took credit for it. So we had platoon of vehicles. The Berkeley concept was having platoons that would drive themselves, and then they split, change lanes, and do other things. So my work was on traction control systems. So how to control the traction, which makes the vehicle move in different weather conditions. So it includes anti-lock braking systems, controlling the traction, which makes the driving better. And then I worked in a company for a couple of years, and then I joined Virginia Tech as a research scientist for 4 years in their Transportation Research Center, and then I became a professor in electrical computer engineering there. And after I got my tenure, so I realized nobody can fire me, so I said, okay, let's do some math. So I did a master's in math and PhD in math. And the research topic, my dissertation topic, was hyperbolic partial differential equations, and why that is relevant to transportation, because that's how we model traffic, which is a compressible fluid. So the first PhD was in microscopic traffic. That was a control of a single vehicle. My second PhD was in controlling macroscopic traffic, where you try to control the traffic as a whole, as a fluid entity. And then I moved to UNLV, and I worked in different areas, like transportation, medicine. Actually, I'm a professor of medicine as well at UNLV, and I'm also a professor of entertainment engineering. So I've done some work in mechatronics, and some work in marketing and auditing as well. Okay, so I have quite a few published books in different areas of vehicle control, robotics, and traffic control. And a lot of the theme involves feedback control of these systems. So when you build a vehicle that is driving autonomously, which means you have sensors, and those sensor values are used so that automatically it is processed in the embedded controller, and then the vehicle will drive itself, obviously, right? So it's a feedback loop where the information, the real-time information, is being used at that time via an algorithm, and of course, so it runs autonomously, right? So it's extremely important, of course, that the algorithm that you're putting in does not destabilize the system. So feedback control, you can say, okay, I'll put this algorithm, but things can get destabilized, especially when they're nonlinear, very, very easily. So stability is extremely important in real-time systems. So that's the primary concern. So when you design these feedback controllers for vehicles and traffic, so these are real-time systems, and they are very, very different types of systems. A vehicle is modeled as a set of ordinary differential equations, depending on the speed, the yaw angle, and then the details of the engine and all other things. But these are finite dimensional systems. You have finitely a vector of the variables that you're interested in, control, which involves lateral movement, longitudinal movement, and all the other dynamics involved. For example, if you're also interested in the vibration and all that stuff, and those variables also come into play, and the engine dynamics, braking dynamics, and all that stuff. But mathematically, that becomes that you have an ordinary differential equation system, and you have some control variables, and you want to design those control variables so that it becomes a closed loop system, so that the output is doing what you want it to do. And for that, you have sensors. But the overall system needs to be stable, needs to give you performance even when your knowledge of the parameters is not accurate, obviously. For example, you have a vehicle. What is the mass of the vehicle is completely different at different times. People of different weights sit at different places, but your controller has to be agnostic to it. It has to work, for all those different conditions. So it has to be robust to parametric uncertainties, and while driving, the uncertainties of road conditions, for example, right? The road surface conditions are changing constantly, and your controller has to perform. So those kinds of things I've worked on, like the feedback controllers for vehicle control, as well as feedback controllers for traffic. So when we talk, and I'll talk a little bit about different types of problems there. So I have, all these books, and I have also some new books that are coming out. And so the modeling phenomenon, as I said, is microscopic, where we can model systems like ordinary differential equations, finite difference equations, finite state machines. If your state is discrete, then they can be finite state machines where the state of the system is jumping from one to the other, so it's still dynamic with respect to time. Then you have macroscopic, where we model the system macroscopically. So space and time are both variables, like in traffic. So that becomes a partial differential equation, and if you can have a deterministic version, or you can have a stochastic version, and then you could have stochastic partial differential equation, and so on. So it depends on what your modeling paradigm is. So how you look at a problem, what modeling paradigm you choose, then how do you design for that paradigm, right? So different kinds of mathematical entities come into play. So, and then there's a mesoscopic modeling, which is in between microscopic and macroscopic, just like in physics. You can study a microscopic phenomena, but then heat you distribute heat, or electromagnetic phenomena again. It's a field that is distributed everywhere. That's macroscopic. Or we study an atom and whatever, but then we can study particles, for example, which are distributed. So it's not macroscopic, because you're not saying it's a continuum function, and it's not like one microscopic entity that you're studying, but it's microscopic, which is spread everywhere. Now that will mean like millions of differential equations. You can't deal with it. So then how do you deal with that? So that's where Boltzmann comes into play. You have distributions, and it becomes statistical physics or statistical mechanics. And if you've been following transportation modeling, for example, of traffic, you also have microscopic modeling of a single vehicle, for example, macroscopic modeling of the traffic, which is a partial differential equation, compressible fluid. But you can also have, and there was a famous Nobel laureate in physics, Ilya Prigogine, who basically was one of the first people to study traffic in the mesoscopic domain, very similar to statistical physics, with distributions of speed and so on, right? So that's the modeling paradigms we have. But even the calculus, changes dramatically when you move from one scheme to the other. So for example, in microscopic, the calculus is your standard calculus, which is ordinary differential equations, your Riemann integration, and so on and so forth. But then when you come to macroscopic, we are dealing with infinite dimensional space. So then convergence of things becomes an issue, and the calculus changes to Lebesgue integrals and so changes like that. And then when you are dealing with stochastic differential equations, for example, when you do modeling like that, we get into Ito calculus, right? That's a very, very different calculus as compared to what you have learned in your regular engineering studies. So even the meaning of solutions, and I'll talk about that because that will show up in traffic modeling as well as travel time dynamics. So, in transportation, I've worked not only with the modeling of vehicles and traffic, but I was the center director for a while. And so, there, as you obviously must be exposed to, that you collect data which involves humans, for example, you do surveys. So, and then you build models, you do stochastic modeling, you use statistics, for example. So, luckily transportation has all of these modeling paradigms. So this chart just kind of gives you an idea of, standard, like there are different types of variables, nominal, ordinal, interval, ratio, and then modeling is involved using those variables. And the modeling can be deterministic, can be stochastic, as you can see. It can be static, where time is not a variable. It's something, for example, you want to optimize a design, and you need an answer. So the time is not involved, right? So, and of course, even traffic assignment, for example, that I'm guessing most of you have studied, can be static traffic assignment or dynamic traffic assignment. So two different types of problems. One is steady state, so time is not moving, and one is dynamically, things are changing, and transient things are happening, and we are interested in those, and we want to control those. So that means modeling can be static, dynamic, and in stochastic also we can have static and dynamic. So here the probability measures and so on. And then here we get stochastic differential equations, Ito calculus comes into play, Brownian motion comes into play. And then in deterministic case, static systems can involve a lot of abstract algebra because the kinds of things we deal with, because our variables are not necessarily continuous. They can be categorical. They can be variables that have ordinal data. There's order. So then if you do optimization, for example, in your high school calculus or whatever, you have a single variable, right? R to R function, and then you can take a derivative on that. But if something is discrete, there is no derivative, but you still have to optimize. So, and some things can have other properties, not just discrete and this, it's more complex phenomena. So that's where abstract algebra comes into play. And you look at functions and mappings and what are the things you can exploit in your engineering designs, right? So transportation involves all of these. Okay, now intelligent transportation systems, we have set the main theme, at least of the work I've done, tends to be that there is sensing, processing of the data, and then actuation of the system. Whether it's in a single car, actuating the steering or the pedal, as well as actuating of a traffic system, right? You want to control the signalized intersection because you're sensing how the traffic is moving, and you want to make changes so that the overall system behaves in a way that we want. So we might be wanting to optimize the performance. And the different types of things can be intelligent vehicles, as we know, traffic management systems, traveler information systems, intelligent planning, and so on. Many, many different things. So then microscopic, macroscopic, the kinds of problems in feedback control setting can be traction control. That was one of my, as I said, PhD dissertation topics. Adaptive cruise control, everybody must be familiar with that. Lateral control, vehicles come with lateral control. I just sat in Dr. Agarwal's car, the Tesla, so that has steering control. And collision avoidance, then communication between vehicles to vehicles, vehicles to infrastructure, vehicles to people, vehicles to X, to anything, right? Or infrastructure to infrastructure. And then macroscopic control problems can be ramp metering. You have some control over that, signalized intersections. You can do diversion. Traffic is coming, and some area is congested, some area is not. So how do you, but again, in real time. So you're getting information in real time, and you're making changes to how you are diverting people in real time. Evacuation, for example, I did some work in evacuation control of pedestrians. So obviously modeling of pedestrians is very different than vehicles because it's two-dimensional versus one-dimensional. And then you want to evacuate, again, as the information is coming in real time, and you want to command people to move in certain ways so you can do optimal evacuation. Another topic I've worked on. I worked on economic control, for example, congestion control, congestion pricing. So you have multiple roads and you can change the pricing, but again in a feedback setting, where as people are coming, the traffic is changing, you keep changing prices to affect how the system is being controlled in real time. And recently, I had a sabbatical for a year, so I worked on many different topics. One of the topics of interest from a city point of view is I studied how a city, the shape of a city, changes over time. What factors are related to that, but as well as the dynamics of that. So again, the differential equations and how in space and time the city boundaries will change. And surprisingly, and very amazingly, there are some mathematical connections of that to traffic dynamics. So I'll kind of present all these things to you. Okay, so now let me talk about one of my contributions, which I actually enjoy, which is the modeling of travel time. So everybody's a transportation researcher, student, and our faculty. Is my guess correct here?
And commercial.
And commercial?
Yeah, industry.
Industry, but in transportation.
Yes, sir.
We are all students, by the way, right? In life.
Absolutely.
Yeah, that's right. When I know I'm not a student, I know I'm dead. Yeah, that's how I know I'm dead. I'm not a student anymore. So, all right. So, how many of your students, like master's students, master's, PhD students? Okay, and except for one, rest are
I've already done all that. I'm past that.
Okay, all right. So, if I ask you, how do you deal with travel time? How do you deal with it? How? Like, what is your model of travel time?
Google Map.
Oh, Google Map is somebody else's engineering. I'm asking you as an engineer, as a student, PhD student or whatever. So if I give you a problem of travel time, how do you do it? What have you studied about travel time in your classes? What functions do you use? What models do you use? What have you learned? Everybody's a transportation person here, right? What have you learned about travel time in your studies? Somebody, come on. Whose GPA is the highest? No, that was a joke. I swear that was a joke. Come on, somebody can answer. So I ask you, let's study travel time. Do you think travel time is important in transportation? Transportation means two things. In fact, maybe one thing. That you want to reach from point A to point B in finite time. Finite. Because if it is infinite time, you know what it means? You are dead. Because you'll never reach the other place.
Identify the level of service of a road.
Level of service. Sure. Thank you very much. At least starting the idea. Anything else? That's all you know. Transportation means movement. Means reaching from point A to point B. And you don't want to take 10 hours, so you want to control the congestion, throughput. And the other thing is it better not be infinite. That means safety. Transportation is about two things. I'm not lecturing about the meaning of transportation. It's just two things. Throughput and safety. You want to move from point A to point B in finite time and not infinite. Number one, that's called safety. And number two, not too long. Means efficient. So when I asked you, what do you know about travel time? There is silence except level of service.
They're shy.
Hmm?
They're shy.
They're shy
Yeah, I think so.
with PhD.
Yeah.
I thought shyness is like, I was an introvert. I still am actually. But, you do research and PhD, that's flushed down the toilet. You can't be, you have to talk. So one more time, travel time. What do you know about travel time? How to compute travel time? So the standard thing is there's a formula. Look at the formula. There's a parameter alpha, beta, c, like how many parameters can you have in a function? And where is this coming from? Which theory? This is travel time. This is a generic formula, and you just then collect data and you match it. Flow. F is flow here. That's it. Even flow is a wrong variable to use, and I'll show you why. Okay, so based on looking at what is travel time is a function of flow, and given as this parameterized model, just a formula, this is the formula. Now go conduct studies, collect data, and find the least square best values of these parameters. That's the theory of travel time, by the way, in this field, which I've spent decades working in. It's amazing, isn't it? That's shocking, actually. Okay, so the thing is, now I'm sure everybody knows this picture, right? So you have density, traffic density, and you have traffic flow. And traffic flow is equal to density times speed. And speed, of course, is a function of density. The simplest model you can say is if the density is 0, you're traveling at free flow speed. And when density is a jam density, the speed is 0. And the simplest model you can build is a straight line. What is the name of that model, by the way? Green shield model, right? Does stand very old. People say, oh, that's not very sophisticated. I don't care which one you use, but at least the boundary conditions will be the same, right? Jam density and this thing, and then whatever beautiful shape you like, use it. I don't care. The bottom line is something like this, right? Concave function. So the thing is, remember, speed is a function of density, right? Is that correct? All right. So if you fix a flow, you get multi-value density. You get two different densities that has the same flow. And two different densities means two different speeds. That means travel time will be different. But that formula is trying to tell you that once you fix flow, your travel time is fixed. You see the basic flaw in this formulation. Okay? Number one problem. So that cannot be. And also, travel time actually changes with space and time. In the sense, if you look at a highway, at a given time, so time is fixed, right? You take a picture, right? And say, okay, now, at this time, the vehicle is at this point. How much time it will take to go from here to here? Okay, so you have fixed your location X, and you're saying, what is the travel time for the vehicle at location X at current time, T0, to reach the end? That's travel time. If at the same time you say, what is the travel time for this one to reach the same end, is different. So it's a function of X. But now you fix that X location, and after 3 seconds, look at a new vehicle that has reached that point, and ask, what is the travel time to the same end location? Do you think it will have changed? Or will it be the same? It will change in general. That depends on, are the conditions homogeneous, right? Or steady state, or they're changing and so on. So in general, of course, travel time is different if you're at the same location. So travel time is a function of time and space, T and X. Anything that's a function of space and or as well as time is called a field. You can have scalar fields, you can have vector fields. A scalar field is that it's a function of space and it's a number. As an example, temperature. Temperature here, it's a scalar field. You can also have vector fields, right? For example, the wind. You give me a position and time, I can tell you the wind, direction, and magnitude. It's called a vector field. Electromagnetic fields are vector fields. So we are talking about a scalar field, which is travel time. So travel time is a field. So on a highway, when I fix T and X, the answer should be a number. Travel time to the end. Okay, number one thing. Okay. And then it changes with time and space. The question is how? How can we build a theory of travel time? Let's start from the basics rather than random formulas and over-parameterized and then collect data, which will of course not be valid anymore after that. You collected data now, 2 hours later, that's changed. So your model, even if you collect data, is fixed. It doesn't change with time and space. It's just, I'm sorry to say, useless. So let's build a theory from scratch, like we are in high school. So if the traffic density is 0, that means you're moving with the free flow speed. Your speed is fixed. So then if the length, your distance is L, time is L over VF, right? Well, that's the easiest thing. We should at least start from there. All right. Then if there are 2 vehicles, then how do we get travel time of both? So let's say the vehicle in front of it there is nobody. So again, free flow speed. But then, depending on the initial condition of the vehicle behind, you get a car following model, right? Its speed will depend on the spacing and the speeds and whatever model that you choose. But the paradigm, mathematical paradigm here, is that you have ordinary differential equation now, modeling the movement of the vehicles. If it's a constant speed, dv over dt is equal to 0, right? Speed is not changing. But if it is changing, so velocity, for example, speed can be a function. In this case, I've taken a very simple green shield based microscopic formula that Vf times, because speed, right? So Vf times 1 minus essentially rho over rho gen. Density over gen density. But density is 1 over spacing, so that gives me an ODE model for the differential equation for the previous one. Now when I solve the differential equation, it only gives me the x values, and then I have to see at what time will it reach this one, and that will be my travel time. So I have to solve this, in fact this differential equation, not for x really, for t, right? Where by the time x has moved from some location to the final location, what is the value of t when I reach there? So that means the modeling involved is solving these ordinary differential equations. So I can find the travel time, right? So a little messy because of course each car travels differently, blah, 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 but that's the theory of it. And then if you have more vehicles, you have an ordinary differential equation for each of the vehicles. So it becomes a system of ODEs. And then again, the idea is to solve them and, find the travel time of the first vehicle where time when x1, its position is equal to L, and so on for the others. Right? So that's the idea behind trying to build a theory of travel time. Then if you have lots of vehicles, right, and now I have to build it, so either I can go into statistical mechanics things, distributions, but statistical mechanics, if you remember your physics studies, there's an equilibrium behavior, but we are interested in how it is changing with space and time. So we're looking at non-equilibrium, when things are transient and changing, and I want to be able to use it, travel time modeling, to then do design of systems and build real-time feedback control systems. Okay? So now let's build a travel time model based on the macroscopic phenomena. It's much easier to deal with lots of vehicles in a macroscopic way rather than microscopic way. Now you can build simulations and you can get answers, numerical answers, but that doesn't give you formulas. That doesn't build you theory. That just can give you outputs. So I'm interested in building a theory of travel time that I can use analytically, okay, and have an understanding of it. Okay, so let's remind ourselves how we build the macroscopic traffic theory. How we built it, it's very simple. So first of all, we don't believe in Star Trek. How many of you have seen Star Trek, the original Star Trek? I'm an old guy. Yeah. Oh, all right. So, with Captain Kirk, right? The original Captain Kirk, who actually went to space. Woohoo! And got depressed by the way. Yeah. So, in Star Trek, what used to happen was, these people stand in one place, they vanish here, and then they appear somewhere else. Now, this still satisfies conservation principle, because the amount of vanishing would equal amount of production. So it's not that the total material is vanishing anywhere. So conservation law is still satisfied, but the local conservation law is not being satisfied. Because locally the mass is, if you take a compact set around it, so locally mass reduced, right? There's no local conservation law. So Star Trek believes in conservation law, but non-locally. In traffic, I think we are in the same group, where we actually believe in local conservation law, where the car which moves here has to be locally moving here, not vanishing here and appearing here, right? At least till now, unless Elon Musk does something different or claims he's doing something different. So we believe in local conservation law, which is very simple, because locally, if you take a section of the highway and say the change in number of vehicles here is how, like in certain amount of time, how many came in minus how many came out. Like in the beginning of the lecture, there were some number of people. Already it has changed. So the question is, luckily nobody has vanished, but some people have come in. So change in the number of people in this room is equal, during that time, is equal to how many came in minus how many came out. In fact, this is a very fantastic idea. It's also used in electromechanics. That to see the change in number of people, I can count everybody here. That's a two-dimensional counting. And then count again at the end. Right? That's a two-dimensional processing once again. But I can get the same answer by looking at one-dimensional boundary, or in this case, maybe even point, zero-dimensional. How many people came in? So I don't need to scan the entire room. I only scan the entry and exit. So change in, that's called Gauss law and so on and so forth, right? That things inside can be found out just from the boundaries, right? It's a Green's theorem, and all kinds of phenomena, Stokes theorem. So all those things are connected to this, studying an area by a change in that, by what happens at the boundaries, right? All right, that's what happens here as well in traffic modeling. So change in the traffic density here. So del rho, I know many civil engineers use K for that. So I prefer rho, density. So change in how many vehicles are here in time is equal to how many vehicles came in minus how many vehicles came out. Vehicles came in at x, and vehicles came out at x plus delta x. So if you take the subtraction of these two, you can see the partial derivative with respect to x, and partial derivative with respect to, of course, time. So therefore, it's just an integral form. Another integral form. Here's the differential form of the conservation law. Change in the density is equal to the negative because, x plus delta x is there, so it becomes del q. Q is the flow over del x, right? That's the conservation law. And q is, of course, the flow, which is equal to density times speed, right? And this is the two-dimensional version of that, because I was building pedestrian models. So there also you do a conservation law, and the movement in 2 dimensions becomes a divergence, right? So del rho over del t plus the divergence of it, how much is coming out in all directions, should be equal to 0, or they should equate each other. Very simple. And then you can say that the flow, for example, is equal to rho times v, and now you're free to choose your relationship. So one exit that reduces our population. So v rho, the speed as a function of density, this is the simplest, the green shield formula, right? So this gives us something called an LWR. Lighthill, Wittem, Richards, 3 mathematicians developed this model. So that's the, a simple example of a macroscopic model of traffic. So this is a partial differential equation. It's a hyperbolic PDE. It resembles, and it's quadratic because the F has a quadratic term in rho. So it's a nonlinear PDE. It's a conservation law, first order partial differential equation. It's hyperbolic. And it is connected to, in mathematics, something called Berger's equation. That's of the same type. Okay, but you can also have different other kinds of models. You can choose your favorite relationship between V and rho. And by the way, these are all direct relationship, local relationship between density and speed. Because these models claim that the speed of a vehicle here is a function of traffic density here. However, you can also claim, for example, that the driver is looking ahead, and the speed is not only a function of density here, but also ahead. Those are called non-local models, and Dr. Agarwal and I have a paper on non-local macroscopic models of traffic. That's another way. You can also say that the speed is also a function of the gradient of density. In the sense, if you see that the traffic density is getting heavier in front of you, what happens to your speed? You slow down, yeah. So not only it's a function of density minus negative k, some parameter, times the gradient of that, del rho over del x. Makes sense. If you do that, then of course the hyperbolic PD will become a parabolic PD. Anyway, so this is the macroscopic model. So what you see is, this is the one I was talking about with the gradient. And this is the same version with the two-dimensional flow. Okay? All right, so let me talk a little bit more about it and then I'll continue. So what is the idea here? So the microscopic modeling that we did, so we had ordinary differential equations. So that means initially, the initial conditions were, if you can run a simulation, for example, or simulations are basically solving the ODEs. So you start with the initial conditions of the vehicle, you have the models for them, and then you can kind of solve them and find the positions at all future times. Right? That's how you solve it. You're given initial conditions, which is a vector. That means positions and speeds of all the vehicles that are present. Right? And of course, boundary conditions, how other vehicles are coming in. And once you have that, you're just solving these ODEs, system of ODEs, and then all the future is based on this model. Similarly here, what is given is the initial function, the entire density function on the highway, let's say, x0 to L. Right? So the initial function is given, this distribution of the density. And what is the PD supposed to do for you? That, like a movie, it will tell you how the density is changing at different times. Whether traffic is going away, or whatever jam is happening, or whatever is happening. So you provide boundaries. So it's similar to the ODEs, except we are talking about, see, in ODEs, I just have to tell you few numbers. Here, how many numbers do I have to give you at any given time t? How many numbers? Infinitely many. So this is an infinite dimensional system. Right? That information is changing at every point. Right? So how can I find the future? That's this, the PD. Just like how do I find the future in microscopic setting? The system of ODEs. Right? So that's the model. Now I try to build the theory of travel time based on microscopic model. Now I will build the theory of travel time using this macroscopic model. So that's the next step. All right. And what will it give me? As I told you, a travel time scalar field that changes with space and time. Okay. Also, like, you can also model, I'm sure most of you are aware, that, when you put sensors for traffic, you can put Eulerian sensors. Euler, the famous mathematician, the king of mathematics. So because he came up with this fluid dynamics model. So Euler sensor means that you put a sensor which is fixed in space, some points, and they only collect data at that fixed position. So the PD that we gave, it was a function of t and x. So if you fix x, you can say, okay, at this x I have sensors. The other way is that one of the vehicles, for example, is also collecting data as it moves. Right? You can also do it in fluids. You can fix a sensor on the ground, or you can have a boat or something floating with the dynamics of the system and collecting data as it moves. But we do that in traffic as well. Right? That is called Lagrangian modeling. And the partial differential equation that you get is given by this. So I don't want to go into the details of deriving it, although it's a beautiful and very fun exercise. But anyway, and then of course you can have smartphone Lagrangian sensors and blah, blah, blah. So a side issue. Now, let's talk about some details about, to build the travel time modeling, I need to understand how traffic changes. So that is extremely interesting, because to solve, how many of you have taken a class, you have studied traffic dynamics, how do they change? How does the PD get solved? How many of you have done that? Because that will give me at least some feedback information about my audience. No one? So if I give you initial traffic on the highway, do you know how to propagate it in the future? No? There's no transportation dynamics, traffic class?
In one class we were what about the PDs, but we were not or how to solve them.
For example, shock waves. You used to learn that even in undergraduate civil engineering transportation class. So everybody knows, for example, how to compute the speed of a shock wave? Yes. Anybody remembers? Okay. Yeah. Okay. Some vertical oscillations are coming. That's a good feedback from the sensor. Okay, at least a few. Okay, one more time. You know how to compute a shock wave speed if there is a discontinuity in traffic, and I can tell you what is the density of traffic here, right? And I'll tell you, find the shock wave speed, right? Okay. Anyway, so what happens is, to solve a PDE, what we do is we convert it into So the initial highway, for example, we say, what is the density at initial time? And I will draw a curve on which I will tell you what the density will be in the future. And I can do that for every initial point. So I will convert a PDE, which is the dynamics of space and time, into I fix the initial position, and now it's a line. If it's a line, that means it has become an ODE. This method has a name. It's called, anybody?
Yes.
Method of characteristics. Okay, so we precisely find that. So what we see is that initially, if you have a traffic density profile like this, so you have a higher density in front of you, lower density of traffic here, and traffic is moving in this direction. The lower density has higher speed, and higher density has lower speed. That means in future time, this keeps coming forward, and density keeps increasing here. And guess what happens in finite time? You get a discontinuity in density profile. Discontinuity. This is called a shock, right? So when we solve this PDE, because of these characteristics which come from the slope of that thing, you get multiple density values come mathematically together, and so all these densities are present there. It becomes discontinuity. So the question is, if I'm telling you that this is the PDE, partial differential equation, which is a model of traffic, how it moves, and I'm giving you an answer which involves a function which is discontinuous with x, could you say that's a solution to this model, to this PDE? By the way, that's a question to you. Do you understand the question? And your answer is no? You shook your head horizontally. No, for some other reason. Okay. Does everybody understand my question? So we have this PDE, partial differential equation. We are looking for a function which changes with space and time. It's a function of t and x, which when you plug it back into the PDE, solves it. That means when you plug it in, the right-hand side becomes equal to 0. That will be the solution of it. And that will show me how traffic is changing, right? So, but what I'm telling you is, and we observe it, the smooth traffic in the beginning becomes a discontinuous traffic like this. Now I'm asking you, can I claim that that is the solution of this PDE? Why not?
Because it's an abrupt.
And why can it be a solution?
Because it's not continuous.
And why do I care about continuity?
Not differentiable.
And what is the problem with differentiability? Because
Traffic dynamics is not linear.
it has nothing to do with linearity.
No, like discrete. So when it breaks into pieces for the
Whatever, yeah.
Yeah.
So why cannot that be a solution? Like, what is the problem?
It's not differentiable.
Oh, very good. And why is that a problem?
Because our model was.
Was a differential equation, a
Very
partial
good.
differential.
Yes, very good. Let me come and shake your hands. Yeah, that deserves a.
Thank you.
Yeah, thank you. Yeah. So, if I say x plus 2 equals 5, what is the answer? What is x?
3.
Thank you. You're scared. Okay, but how do I say this is correct? Because I'll take that 3 and plug it into the left-hand side of the equation. I'll say 3 plus 2, 5. Oh yeah, it is a solution. So if I'm giving you something which is discontinuous like this, and trying to plug it into the differential equation, I can't, because it doesn't differentiate. So it cannot be called a solution to the PDE. But traffic gets shocks. So how can I say, and this is exactly what I want this to be the solution, because that's what we see. And the model is this. And not only that, I want to know what happens after that. Like first the shock is formed, and then what will happen after that? Because that's the future of traffic. I mean, literally, your initial conditions. So I want to be able to use this and continue it. How do you do it? So that, the mathematics comes into play. These are called weak solutions. So weak solution of the PDE, which allows discontinuous solutions and helps them propagate forward. Okay, so one issue is that I'm trying to get too many values. Same thing happens in a wave of water. If you go to the beach and everything, the water starts single valued function, and then the wave can do this, multiple values. Okay, that's also creates shock and so on. Right, so we need a theory for that. Not only that, when you draw these characteristics, so if, for example, when a green light, the red light turns green, if you draw the characteristics, there will be a region of this where there are no traffic densities coming in the future. I don't know what the traffic density will be. Right? So when you allow weak solutions, okay, I solve this problem, but then, I have no solutions, or there are multiple solutions for that rate of the other condition. Yeah?
We have 15 minutes.
15 minutes. Okay, let's move forward. So here's the discontinuity produced. So we have to change the meaning of the solution. So that brings a higher level of meaning called weak solutions. The calculus required brings us to something called measure theory and so on. And then we allow shocks, and you get regions where there's no traffic density. We don't know how to produce it. And then we say, when I say a solution of the traffic density, it should be such that if I had changed the original partial differential equation, which was a hyperbolic PDE, because it produces these problems, if you add a viscosity term, that means if I had chosen my speed to have that density relationship, it would have become a parabolic partial differential equation, like a heat equation. That has solutions. And if you make that heat to go to zero in the limit, you get the solution to this hyperbolic PDE. It's called a viscosity solution, vanishing viscosity solution. That is a solution to this traffic dynamics problem in a macroscopic setting. And boundary conditions become important and so on. Okay, so then there are shock, so these are just some pictures about that since only 15 minutes are left. Now I'll give you the travel time dynamics. So now the story is like this. So we have time and x, and we have traffic. These characteristics are formed, and given the initial traffic conditions, traffic density, I can evolve the future densities. Okay, so now I have to find out, so I can see how the densities are changing, and I want to be able to say what is the travel time for any vehicle which was at position x at time t. How do you get that? So what I do is I say that, let's say there's a trajectory of a vehicle, like moving in time and space like this. So on that curve, as x of that is a function of time, its position is changing in function of time, what is it following? So for that vehicle, travel time, I'm calling it uppercase t, which is a function of the lowercase t, which is the actual time. The travel time to the end is the uppercase t. So for that vehicle, whatever the travel time was for that vehicle at one time, so after, to reach the end, after it has consumed 1 second, what is the travel time to the end now as compared to before?
1 minute less.
Or whatever, 1 second less or whatever time. Yeah, simple. So that means the full derivative of the travel time function, d of t, is there a, oh, there's no board. So full derivative, because travel time is a function of t and x. So if you follow the trajectory of the vehicle, in 1 second, its travel time would have changed, reduced by 1 second. So its full derivative, dt over d lowercase t, is equal to -1. But this travel time t is a function of time and space. If you remember your calculus, you want to take a full derivative of something with respect to lowercase t. It is a function of two variables, and the second variable x is a function of lowercase t. What rule do you use? Chain rule. So when you expand the chain rule, the partial derivative of t with respect to t plus del t over del x times dx over dt. What is the dx over dt for this vehicle? The speed, which is a function of the density in front of it, or there. And that should equal -1, plus 1 equal to 0. This is the partial differential equation, that is my contribution to the field of travel time, where travel time changes with t and x. Now this partial, it's also a first order partial differential equation, and now the system, this is not an independent PDE. You can't solve it without, so this is the entire system now. So it's a system of two PDEs here. You have the density one, the LWR for example, and then associated with it, this. So basically you have to solve the densities, and then you can solve this, where v is given by this, and now you can give travel time for every vehicle at every time. I can solve it for you, right? This is a macroscopic travel time dynamics model. Now again, when you look at this one is also first order. And the structure of it is very specific because it involves the gradient, in this case of course, partial derivative with respect to x, but if it were in 2 dimensions, it would have a gradient here. So it has a name, it's called Hamilton-Jacobi partial differential equation. So this travel time dynamics is a Hamilton-Jacobi partial differential equation. And the solution of this can also have discontinuities theoretically. So the solutions of this also have to be viscosity solutions, that we allow discontinuities and so on and so forth. So I've written quite a few papers on this, mathematically inclined papers, that develop the theory of travel time dynamics and then prove the properties, mathematical properties. But the real part is not that, not the mathematical parts, of course. It's important. Then how to use this in your design. Because there is no model for this before this. And should we design our systems for optimizing travel time? Yes or no? Of course.
Yeah.
And which formula are you going to use? That previous one, which doesn't change with space and time. With some alphas, some beta, and some gamma somewhere. I don't know. How? Travel time changes all the time. You need a model for it. This is it. And it's been derived from basic principles. There's no magic. Right? This is straight derivation from fundamental principles. So, and then transportation networks now. So for example, if you come from traditional transportation engineering, you have done traffic assignment, haven't you? When you do traffic assignment, there are two types of traffic assignments. Can you tell me which they are? Static and dynamic. Yeah, I mentioned that. Very good, at least you got that. And even when you fix static, there are two types of optimization problems you can solve. Yes, please. Who said that? Say it with pride. Yeah, oh, professor. Ah, that's cheating. Oh, I was like getting so excited when a professor is speaking. That was like award-winning professor. That is not fair. That is open cheating. Yeah, user equilibrium and system optimum, right? And what is user equilibrium? And if you know the details of that, it's a very beautiful problem, by the way. It tells you that travel time is same in alternate routes. Travel time is same. Travel time, you don't have a model for that. And I've read those books. They use that model. Okay, and then same with user equilibrium. You're going to use that model, and then you do dynamic traffic assignment. So you are at least realizing the traffic is not static, it's not steady state. We want to understand it in a dynamic setting. And then you're going to use that travel time. How? So now you make the models with this travel time in that system. Okay, in networks. And now you can design your feedback solutions to traffic with the proper travel time. It's challenging, but that's why we are here, to have fun with challenging problems. All right, so all your optimization, optimal controls need to be done with that. So in India last year, I did some new work in travel time in heterogeneous traffic. Because here it seems like when density is fixed, travel time is a function of that, because speed. But if you go to a place like India, so even if wherever you are, but if you are an auto or a scooter versus a car, even with the same position, your travel time is different. So you have to now change the model, have multiple species, and you'll have different PDs set up like this, and then you can create travel time for each kind of vehicle as a function of DNX. So that's the next level, which I've already sort of 75% done. So instead of green shield model, it becomes a three-dimensional model, and a lot of fun. And then the applications. You want to control the traffic light, you want to control the ramp metering, you want to control the diversion. You do it with travel time, dynamic travel time. Bring this in. I mean, I've given this lecture many places. I don't see anybody doing it. But I'm trying. I'm a cheerleader. Let's use travel time dynamics in solving these problems. Right? Because it's not based on some empirical weirdness. Okay, that finishes this. Except, don't go away. I want to show you, it's open. So I told you I did, actually I'd gone to IIT Bombay, that's where I did my undergrad. So I spent a couple of months last year there. So this guy picks me up from the airport, and I'm like, what are you doing? So he said, I'm doing PhD in, how cities evolve. Like, hey, sounds good. Tell me all about it. So he started telling me. So I said, you see the city evolving, so it's the shape, the boundary that's changing over time. So it's an interface that is developing. So I said, this sounds like Huygens principle. How many of you remember Huygens principle? Does it ring a bell?
Yeah.
No, everything rings a bell to you. I'm asking everybody else. This bell is ringing constantly. I mean, that's how you should live. But how many other bells are ringing? Huygens principle. H-U-Y. You wanted to do physics. Huygens principle. It is not a wave. Every point in the front of the wave becomes a source of the wave. And then you can take the envelope of that and see how it evolves. So like immediately you can think of every point of the boundary of the city is evolving at different speeds, and we can see how it changes. So we can bring in the Huygens principle into this evolution. So what I found there was, so I kind of worked for 1 month and again came back, so got some papers out of this. And this is the latest one I'm writing. So this is the Huygens principle, essentially. Every point, is creating a source, point source, traveling in all directions, and the envelope keeps moving and changing. And of course, speed is different at different points. And again, in city development, it depends on which region will develop more or less. That depends on other variables. Distance to school, distance to highways, and so on and so forth. So you can do the modeling of speed based on those variables. But then once you know the speed of movement, how can you get the kinematics and the dynamics of this evolution? So for that, it's Huygens principle. And what I found to my delight, utter delight, that it follows so imagine like this. Imagine a surface like this, okay? So the z-axis is time. So at t, if you slice this surface, what do you get? A curve. And that curve is the boundary of the city. And then if you go to the future time and slice it, that curve, that surface has changed, so that you have a new boundary. So the slicing of different boundaries creates a surface. And if you do the mathematics behind this Huygens principle, you find out that the partial differential equation is this u is a function, basically it's time, so it satisfies this equation. Again, the gradient is involved in this. So this is also essentially like a Hamilton-Jacobi equation. So this is a very specific name called Eikenal equation. And then I can also get the characteristics of it. That means I can get a ray and see that this point in the boundary, how will it evolve? That will have its own ODE, and I'm sure I don't have time left, because the derivation of this, again, is so pleasurable. Okay? And I mean it. This is not a joke. And there are more details, but the bottom line is, look. So, look at the top part. So let's say this is the boundary of, the city boundary like this. So city is like this, like this. And if the evolution is going in the normal direction, right? So whatever, if it's like this, it's moving like this. So what happens is, you have those multiple characteristics coming at one point, and look, something that was smooth became pointed. Same thing as the shock wave in traffic. We get a discontinuity, it's not discontinuity of the derivative. It's not smooth anymore. But we have a PDE to solve. It's the exact same thing. Same concept happens in city evolution. And here, when it was evolving like this and starting with a triangle, we have characteristics going this way, and there is nothing here, just like the traffic changing from red to the green. I don't have an answer what will happen in front of me. So I have to do this rarefaction and viscosity solution. So that was fantastic to see. That the idea that we had to use to solve traffic is involved in studying how a city evolves. Same thing comes into play. That's fantastic, beautiful. Made me very happy. I think, should I finish now? It's time? All right, my boss has told me that I need to stop. There's a funny thing. So he says, I'm his advisor to strangers, but then he tells me I've never advised him. So then, I don't know what kind of advisor, the name I should have. Anyway, but he's always been my boss. So he says stop, I stop.
Okay, we have time for quick questions.
Yes, actually, we have heard that you are a very nice singer. So would you please?
Okay, let's wait for the next question.
Oh, one question I have, is there a possibility of having non-convex optimization problem in traffic domain?
So let me explain. When you talk, first of all, of course, the answer is yes, but wait, let me be very